Hello everyone. So, in this part, we'll be mainly talking about X-rays, their production, and we will discover how this whole process works. So, you might be wondering what is this small box in front of you. So, let me tell you that this is the source of the X-rays. This is an X-ray tube. It consists of a high voltage supply connected to a vacuum chamber inside of a leading shielding, containing a filter. This vacuum chamber is containing a cathode filament and an anode, also known as the target of electron. Now we will be discovering more about each of the components of this X-ray tube. Let's begin first with the cathode filament. This cathode filament, its main purpose is to produce electrons. It is a filament of metal with high melting point that is negatively charged, so electrons accumulate on it. When the filament is boiled, electrons are boiled off. This process is called thermionic emission. More electrons per unit time means more X-rays per unit. Let's move to the high voltage field. The main purpose of this high voltage field is to accelerate electrons. The electrons produced at the cathode will be accelerated towards the anode. One of the most important components in the X-ray tube is undoubtedly vacuum chamber. Its purpose is to remove obstructions to electrons, as the air molecules block the path of electrons. Electrons unobstructed reach the target or the anode with a high kinetic energy. Those electrons then reach the anode, or as we said earlier, the target. It is there as a converter, as it will convert electrons' kinetic energy to X-ray photons. Once the electrons collide with the anode, they will decelerate and they will produce X-ray photons and heat, which percentage is 99%. The anode material is customizable, so different materials means different spectrum of X-rays. One of the most important components of the X-ray tube is the lead shielding. Its role is to contain stray electrons and X-rays. It protects the patients from the harmful scattered radiations, as these radiations are absorbed. Now comes the role of the filter. As we saw earlier, it is connected to the bottom of the lead shielding. It is a thin sheet of aluminum. Its purpose is to absorb the low energy photons, while the high energy photons will get through the filter and they won't be blocked. Now, after we discovered each of the components or elements of the X-ray tube, let's move to how this whole process works when it comes to a patient. In other words, how these X-rays penetrate the body of the patient. So, after those X-ray beams are released from the filter, they are absorbed by only dense body tissues as bone. As it is a high frequency beam, we use a radiographic film which is placed behind the patient, and this latter is placed between the film and the X-ray machine. The machine then focuses the X-ray beam on the specific body part. As the X-ray energy passes through the body of the patient, the photons reach the film and cause a chemical reaction. So the area where the X-ray energy passed through the body becomes black, where the area where the energy is absorbed appear white, and this how we will get the X-ray, clear X-ray imagery. To wrap up, in this part concentrated on X-rays, we discovered first the X-ray tube, which is the source of X-rays, and then each one of the elements of this important box. And then we discovered how it is applied to a patient and what's the outcome of this operation.
As of my part, I will expand on MRIs, magnetic resonance imaging. First, we need to answer the following question: what is an MRI? Magnetic resonance imaging, MRI, also known as nuclear magnetic resonance imaging, is a medical imaging scanning technique used in radiology for creating detailed images of the human body. Unlike other electromagnetic scans, MRI requires no exposure to radiation and often permits clearer pictures. MRI scans are often the technique of choice because they now produce some of the clearest images of a brain. However, not everyone can undergo an MRI scan. The magnetic fields generated in an MRI scan interfere with electrical fields, so people with pacemakers are not candidates for an MRI. Neither are people with metal in their bodies, such as surgical clip or any metal shaving in any part of their body. Just throwing a metal object in an MRI would result into this. Secondly, now that we have defined an MRI, we need to know what they are composed of. An MRI scan is essentially made of strong, powerful, superconducting magnets, radio waves, and a computer to create detailed images. The major components of an MRI scanner are the main magnet, which polarizes the sample, the shim coils for correcting non-homogeneous particles in the main magnetic field, the gradient system, which is used to localize the magnetic resonance signal, and the radio frequency system, which excites the sample and detects the resulting nuclear magnetic resonance signal. The whole system is controlled by one or more computers. So, for the most crucial question, now that we have defined what is an MRI and what is an MRI made of, we need to know how does an MRI work. MRI is based on the phenomenon of nuclear magnetic resonance, or NMR, and this will be the most crucial concept, or what the MRI technology is technically based on. So, what is nuclear magnetic resonance? It is the physical concept that certain atomic nuclei demonstrate the ability to absorb and re-emit radio frequency energy when placed in a magnetic field. First, certain atomic nuclei tend to behave like tiny bar magnets. And this means that in a magnetic field, the nuclei will align with the field just like a compass needle likes to align with the Earth's magnetic field. What an MRI does is send in a radio frequency pulse into the body to knock off the nuclei out of alignment with the field, and this is where the NMR phenomenon kicks in with the nucleus, which will precess about the magnetic field giving off its own RF signal, its own radio frequency signal. And in the process, this is what the scanner detects. But it doesn't last forever. After a certain amount of time, the radio frequency signal from the nuclei dies away. But the amount of time it takes for the signal to die off is different from tissue to tissue. So this is called T2 relaxation. And after T2 relaxation, it is one method of providing tissue contrast in images. Finally, the nuclei will eventually realign with the magnetic field, and the amount of time that it takes to do this is called T1 relaxation. And the MRI machine will basically repeat this process over and over again until it has enough signals to produce a diagnostically sound image. To one equation, which is the frequency of precession is proportional to the magnetic field strength. The Larmor equation.
Gamma knife surgery, a technique used to attack tumors in the brain, and before understanding what this is, one would need to first be aware of the basic concepts pertaining to radiophysics. I wisely start off by introducing some of the fundamental formula that are used within this concept. E equals hv, E being the energy, h Planck's constant, and V the frequency of radiation. E equals mc squared. I leave up to you to guess what it is. It is necessary to quickly introduce ionizing radiation, which refers to radiation of sufficiently high energy, being able to dislodge or disrupt bonds between atoms. This is the effect that we will use to force upon atoms to produce the gamma radiation for the procedure, also known as radioactive decay, namely using cobalt-16, which produces the gamma rays but also loses electrons. When electrons are emitted from a sheet of metal, After light is shined on it, it's called the photoelectric effect. As photon strikes a metal, the photon is absorbed. The photon causes an electron to be released from the metal, and the photoelectron is sent out. For the electron to be emitted from the metal, a certain amount of kinetic energy is needed, and the following equation is used to find out if electrons will be emitted, and that is kinetic energy max equals to HF minus HFT. Pair production. It is the conversion of radiation quantum in an electron and a positron. Now that we have seen the formula that can be used, E equals mc squared, and kinetic energy is half mv squared, we are properly able to move on to gamma knife surgery and see the relation it has with all of these other concepts, and finally bring a better understanding of this technique unto you. Gamma knife gamma radiation is of course non-particulate electromagnetic radiation to be considered either as waves or photons. The gamma radiation produced by 60 cobalt has two energies reflecting two distinct radioactive breakdown pathways. The gamma radiation from these two reaction series has an energy of either 1.17 or 1.33 mega electronic volts, depending on which radioactive breakdown pathway is being considered. Most of the interaction between radiation and irradiated tissue can be expected to be mediated by degree pair production. The energy level of this radiation is sufficient to give it a high power of penetration. It has a low linear energy transfer. The narrow beams essentially to the technique are produced by the construction with forces the radiation through coulometers in the form of small metal tubes mounted in the machine's helmet. The size of the coulometer is defined in terms of the diameter of the 50% isodose around the center of the target.